in this lecture, I will continue with my description of the long laser chains that we were talking about last time, and and this chain which will be used for inertial confinement fusion. Okay. So, in that we had seen a whole lot of laser amplifiers that amplifies the seed pulse. Seed pulse means the initial pulse which has all the properties that you desire, and these properties of the seed pulse has to be conserved while it is passing through these amplifiers. That is one of the conditions, and also you are extracting the maximum energy that you can from each amplifier. Now, what we had seen in those set of amplifiers was that the chain grows longer and longer, and with it the equipment becomes a little more complicated, and some of the large equipments that are used, that means the large glass ND glass rods, we were sticking to the ND glass part, ND glass rods that are required. It is more and more difficult to manufacture these. So, one has to do some smart architecture for the amplifiers in order to save, say, space, save energy, and have a smaller lab. Okay. In fact, most of these were not in very small labs, they are as large as a big factory. So, let us see if that can be reduced, at least the size. So, here as you can see here, this I talk about, this is the amplifier, the one shown in the red line here. This is the amplifier, and this is one architecture of the amplification system. So, here you have a Z shaped beam which is passing through the amplifier. Z shaped in the sense it is a beam here which has a small spot size. It goes through the amplifier here, and this is a mirror here. It gets reflected off that, and it passes through the amplifier here again. It gets reflected off this mirror here, and then passes through the amplifier once again and comes out as the output beam. So, here what we have done is, instead of having 3 amplifiers for this beam, and this beam, we have crunched it into one amplifier and making the maximum use of the active medium here. Okay. If the beam were to pass through just this part of the amplifying medium would just go waste, and you would be just adding another amplifier. And here it passes through another part of the amplifying medium, and it is able to extract gain in this. So, this is one of the architecture, and another architecture of an amplifier is this here. This is the amplifier again shown in red. So, here what you have is, you have this input beam shown in light blue which is travelling along here. It comes across a mirror which is a concave mirror, and obviously with this concave mirror the beam will expand, which is shown here. It goes here, the beam will expand, it will show here, and here I have a concave mirror, and the beam gets collimated and passes through the amplifier again. So, here also I have 3 passes, here also I have 3 passes, but the 2 architectures are a bit different. So, here in this case, not only is the beam expanding, so energy per centimeter square reduces. So, that again is a big help, as I had explained in my last lecture. And at the same time, this part, this gray part, this part of the amplifying medium is being used to extract gain. This part of the amplifying medium is being used to extract gain. Okay. Similarly, for here, this unused, if it were not expanded, this unused part of the amplifier gain medium is being used. Okay. So, this is one way. So, these two kind of architectures reduce the number of physical amplifiers that you have to add in the chain. Okay. Now, what happens is, so what you have done is, if I just show it here, instead of having 3 amplifier chains like this and the beam just passing right through, you just have one with 3 passes. Okay, this is easily understandable. Now, all over the world, I have just, people have built, researchers have built such kind of lasers, and I just tabulate them in this table here. Okay. And these lasers that I am referring to are all in the nanosecond pulse length scale. Okay. So, when you have this nanosecond pulse length scale, you can call it a short pulse. It falls under the category of short pulse. So, NIF, National Ignition Facility at USA, has built a chain with a pulse length of 10 to 20 nanoseconds at the output, and the energy output is 1.8 megajoule. This could be over 2-3 beams, and the peak power achieved is 500 terawatt. Okay. So, we are interested in the peak power. Finally, we are interested in the peak power and the intensity that will fall onto that tiny target which holds the deuterium and tritium. Okay, that is the whole idea. So, we are interested in this peak flash of light. Okay. So, most of the interest is in the peak power. So, terawatt here, they have got terawatt. Terawatt means 10 to the power 12 watts. Okay. So, the energy is in 1.8 megajoules. Mega is okay, and if you divide by the pulse length, you are getting the peak power. Okay. In case of Gecko laser of Japan, they had a 1 to 10 nanosecond pulse and produced each beam produced 2 kilojoules of laser. Okay. And the peak power obtained is 0.2 terawatts. 0.2 into 10 to the power 12 watts. Okay. Now, in case of the Vulcan laser, which is a laser built in the UK, it had a 1 nanosecond pulse and 500 joules energy output from the amplifier chain. These are all really huge systems, very, very big and long systems. Okay. And then they obtained a 0.5 terawatt power, better than these. Okay. And then Lully 2000 of France had a 5 nanosecond pulse laser and 1.5 kilojoule output energy, giving somewhere around 1 terawatt of power. So clearly for the nanosecond laser chain, primarily devised for ICF, that was our primary thing. You can use it for many other researchers, of course, but the primary thing is for ICF, are also being used for high energy density physics, okay, and plasma science. Here the longer pulses are necessary to compress and heat the material without permanently dissipating the target integrity. Okay. So, as all these chains were definitely used for the ICF part, so by target integrity it is meant this way, that this was my small pellet target, okay, and you had laser beams from all different sides. And since you had all these laser beams, they had to fall exactly simultaneously, as I had said before, simultaneously in order to produce that compression required and produce the ignition of the deuterium and then the burn. But clearly none of the labs have obtained a sustained sustained controlled fusion. Okay. None of them have got break-even condition. So, there is definitely a problem, and you do need nanosecond pulses. You do need nanosecond pulses. So, it was prudent of all these labs to build nanosecond laser chain, because the laser stability and the plasma stability, the plasma that is formed here, is brought about by these nanosecond pulses. Okay. But at the same time, you need high peak powers. Okay. So, there is no dispute about the fact that you need high peak powers. Though many of these other problems have to be solved, the instability part has to be solved, the simultaneous compact push for the pellet, that part has to be solved. So, many of these problems have to be solved, but the high peak power remains as a necessity. So, now now what has happened is many of these lasers which I have shown in this table have been either retired or they have been modified to go into the newer category of laser chains, newer category with the newer technology involved in it, in order to get higher peak powers. Okay. That has been done. Because many of the amplifiers, whether in actual physical amplifier and the way it has been pumped and all that, they are not waste. You can reuse them, and all that knowledge that you have gathered while propagating a nanosecond pulse length through these amplifiers is invaluable. Okay, in order to make a transition into this new technology. Okay. The new technology is this, that you need to make shorter and shorter pulses. Then if you make a very short pulse, then the energy output itself, you make a short pulse, your peak power will just rise up whether you extract more energy or not. Okay. You just shorten this pulse and you will this will go up beyond terawatt, 500 terawatt level. So, I will just write this once again, because this is what we will be using now most often. So, peak power is equal to that energy, total energy extracted, divide by the time. Okay. Now, this laser beam is again focused into a tiny target like this. So, the laser beam has to focus here, and once you focus the laser beam, the intensity goes up. So, we have to talk about the intensity too. So, what do I say? Intensity is equal to power divide by area, how small you can put it. So, it is generally given in units of watts per centimeter square. Okay. So, we will be talking about intensity, we will be talking about peak power. This is the total energy. Energy is of course joules, peak power is given in watts, joules per unit time will give you watt. Okay. So, let us go ahead to see how we can increase the peak power by reducing the pulse length. That is what the new technology is about. Okay. And many of these lasers which were built before have been modified, okay, into these the newer kind of lasers. So, let me see. So, the need is for more peak power. More peak power in the shortest possible pulse. you concentrate all the energy into the short pulse, and then you focus it to obtain a very large intensities. Okay. So, this is the idea to be followed. You shorten the pulse, you extract energy, and then you focus the beam to get very, very high intensities. So, energy extraction can be done from rod amplifiers, disc amplifiers, multipass amplifiers and regenerative amplifiers. These are all different kinds of amplifiers which make the total amplifying process more efficient, and the sizes also become smaller. You know, you can fit everything into a smaller space. Okay, so we will just see what these amplifiers are like, and then you have these large energies, and you have to preserve the bandwidth in the amplifiers. So, bandwidth also plays a very important role in this amplifier chain. So, let me tell you a bit about these rod amplifiers, disc amplifiers. Just here. So, in case of these are all rod amplifiers, where you increase these are rods, ND glass rods. You increase the length of this rod, you increase the width of this rod. So, you make them larger and larger. Okay. And then you have the disc amplifiers which are similar to this, but only thing that thickness part is small. You have increased the cross sectional size, and these are the disc amplifiers. Then you have the multipass amplifiers. The multipass amplifiers is something like this one which I showed you here, which has a Z thing. So, you have one mirror here and one mirror here. So, it is more than one pass, that is why it is multipass. In fact, if you can place many more mirrors like this, suppose you have a mirror here, you can put a mirror here, however you can place that, you can put a mirror here, you can put a mirror here, here and here. So, you can have a multipass beam like this, more than 3 basically. So, these are multipass beam. So, you are making the energy extraction process from amplifiers much more efficient. Then you have the regenerative amplifier, which is specific to this ultra short pulse amplification. See, we have already come to the realm of ultra short pulse. Okay. So, in case of the nanosecond pulse, we called it the short pulse, but now we will be dealing with picosecond and femtosecond generally. So, it is an ultra short pulse, the pulse is in that range. Okay. So, let us see what are the issues with ultra short pulses that make the amplification process better or worse or problematic. That is what we will see during the course of this lecture. Okay, so let me tell you about the regenerative amplifier. So, in case of ultra short pulse, the pulse that comes out of the oscillator has a very small energy. So, you generally need to pass it through a regenerative amplifier, which is somewhat like an oscillator. So, the oscillator may have 40, 50, maybe around 70, 80 round trips, while in case of a regenerative you might have 10, 20, 30 round trips. Okay. So, basically it is passing up and down here, it is going out and coming back, somewhat like a round trip, but lesser number of round trips than in an oscillator. So, this is a regenerative amplifier. Okay. So, we will come back to this slide, and So let's just, before we go further, let's just go through the trajectory of the long amplifier chains. Where was the bottleneck where more energy or more peak power could not be extracted? Okay, where was that bottleneck and how it was overcome? So if you see here, somewhere around the 1960 or between 1960 and 1970, you had this free running laser. Free running means there is only one pulse which is coming out, or so there is no other control, there is no modulation, it is just one pulse that comes out, and it happens on its own within the oscillator. So that is called a free running laser. Okay. So I write it here, free running laser, and the pulse length is in the microsecond range in case of a free running laser. So then the peak powers that were achieved were in the kilowatt range. Kilowatt means 10 to the power 3 watts, okay, the peak power achieved in case of this free running. Okay. Then within a short time, the Q switched laser was invented. Try to recollect the Q switch laser that I had described before. In that you do get nanosecond range pulses, okay, that increase the peak power to a megawatt range. Okay. So here, so this is around megawatt, 10 to the power 6 watts here. On the y axis I have given the power in watts, peak power in watts, and the x axis is of course the number of years over which this has been taking place. Okay. So that is that. Now after the Q switch was invented, within a short time, few years, the mode locking was invented. So in mode locking, the output pulse is much shorter, that is in the picosecond range. So the peak powers that you will get is in the gigawatt. Gigawatt is 10 to the power 9 watts. Okay. So here it is the mode locking, and this is C 10 to the power 9 watts. Okay. Then for over 20 years, nothing much happened. Surely there was a bottleneck in the technology itself. So something new had to be invented before the peak powers from these laser chains could be increased. Luckily, after that 20 years, chirped pulse amplification was invented. Okay. And you got pulse length. I will explain what is chirped pulse amplification. For the moment, just call it CPA. Okay. So in this case, you get pulses in the range of femto-second. The moment you get pulses in the range of femto-second, the peak power becomes peta-watt. Okay. Peta-watt is 10 to the power 12 giga, 10 to the power 15. Okay. So that is peta-watt laser. So you've gained an energy of that kind. Okay. So it was invented somewhere here, somewhere in 1985. Okay. It was, and the Nobel Prize was given for that invention to Gerard Moreau and Donna Strickland. Okay. If you remember my first lecture there, I have just mentioned their name. And it is a 1985 paper which they published, and because of this ingenious technique that they developed, the peak powers could rise up to this level. Okay. So that is that's the beauty of this thing. So so the peak powers could go up. So what I have to say is, you have a seed pulse. Okay. And this seed pulse goes on to the amplifiers, the chain of amplifiers. But the property of the seed pulse which you have generated in this oscillator has to be preserved as it goes through. So that is what we will see in the following lectures.